Hello, Professor Lehman. This is presentation number 3 for Brady Johnson. And as you know, we're going to use combined loading to find the principal stresses and maximum shear stress at point A along the beam given. So I already took the time to draw a force diagram showing all the known forces acting on the beam as well as the reaction forces along the axes I call them the unknowns because we don't know them yet. And so the first thing we're going to do is we're going to use those loads that we have given. Let's start the 750 newtons, the 500 newtons, and the 10,000 newtons. And we're going to use the two vectors, the position vector and force vector, to find our moment vector, which will help us find those unknowns on that force diagram, which will help us for the remainder of the problem. So we're going to first find our position vector, which is going to be the position where the force is located in relation to the axes. We're going to find our force vector, which is just going to be the direction the force is acting on. And then we're going to find our moment vector, which is going to be the cross product of our position vector and our force vector to find the moments acting on each axis. And so to start off with our 750 Newton load, that is 180 millimeters from point A that we're working with, I decided to change it to meters, so that's going to be 0.180 meters. And it's also going to be from that point up 16 millimeters, or 0.016 meters. And it's not moving any direction in the K direction, in the Z direction. For the force, it's going downwards in the Y direction, so we're going to have a 0. We're going to have a negative 750 newtons and another 0. For the 500 newtons, it's going to be 220 millimeters, or 0.220 meters away from A. And it doesn't move in the Y direction or in the Z direction. And this one is going to be a positive 500 newtons in the Z direction, so we're going to have a 0, 0, and a 500 newtons. For the 10,000, it's going to be along the same exact point as the 500 newtons, so we're going to have the same exact positions. And then for the force, we're going to have 10,000 newtons acting positively in the X direction, and then we're going to have 0 along the rest. And so now what we're going to do is we're going to find our moments. And so how that will work to show for one of them to find our 750 Newton is we're going to have both of our vectors, our position vector right here, and we're going to have our force vector. And we're going to find the cross product, which is going to be multiplied the 0.016 times 0. And then you're going to subtract it by our negative 750, or 0. So that's our I, which is going to be 0. And that's going to be minus our 0.180 times 0. And that's going to be minus our 0 times 0, which I'm just going to write 0. And so that's going to be our J, which is also 0. And now it's going to be plus, and it's going to be finally our cross product between our I and our J, and that's going to be the 0.180 times our negative 750 minus 0 times 0.016, which is just 0. But we do finally get a number, and so that's going to be our negative 135. And so for time, I'm not going to do that for each one, but that's how you would find the cross product for both our position and our force vector to find our moments. So our moment for 500 newtons is going to be 0, negative 110, and 0. And then for our 10,000, it's just going to be 0 across the line. And this is going to be in Newton meters. And so now what we have come to find is through our force vectors and our moment vectors, we were able to find our Rx, our Ry, our Rz, as well as our moment in the X direction, moment in the Y direction, and our moment in the Z direction. So how this is going to work is because this isn't moving, whatever we got from our force vector and our moment vector, it's going to be negative of that. Excuse me. And so for in our I direction, our x, we're going to have 10,000 newtons. So for our Rx, that's going to be negative 10,000 newtons. Same thing for y, negative 750 is going to be 750 newtons. And for our 500, that's going to be a negative 500 newtons. For our moment, it's going to be the same thing. For our x, we don't have actually an x. It's going to be 0 newton meters. For our y, we're going to have negative 110, which is going to be 110 newton meters. And then for our z, it's going to be negative 135, which makes it 135 newton meters. And so what that does is now we have those to figure out all of our different stresses and our shear to find our principal stresses. And so what we do know is, because the x-axis is going through the neutral axis of the beam, going along the beam, we know that our Rx is going to be along the longitudinal part of the beam. And so our Rx is going to have an axial stress. And so we're going to create a cut diagram. And this is going to be in the x direction. This is going to be in the y direction. This is going to be from looking sideways of our picture. So what we get is we have to add our negative 10,000 newtons in. That's going to be our Rx. Since it's negative, it's going to be going in the negative direction of x. So we're going to get 10,000 newtons, which is putting it in tension. And we're going to solve to find our stress, which is going to be our axial stress is going to be P over A, which we have P to be 10,000 in tension newtons. And we have our area, and our area is just going to be our box right here. I'll draw the cross section looking inward from the x direction. And so this is going to be, this length is 60 millimeters, which is just 0.06 meters. Our length here is going to be 32 millimeters, or 0.032 meters. And that's just base times height. So now we're just going to have 0.060 times 0.032 meters squared. And that comes out to have our stress equal 5.208 megapascals. And so now we're going to draw our stress blocks. Can you still see? Great. And so we're going to draw first one, second, third, x, y, x, z, and then our zy. And so this is an x direction, so we're going to have intention right here and right here, which is going to be our 5.208 megapascals. 5.208 megapascals. Great. So now what we're going to do is we're going to find our transverse shear using our R of y, going in the y direction. And so we're going to have our R of y, which gives us our transverse shear. So we're going to make another cut. And this is going to be in the x direction, this is going to be in the y direction, so same look, same viewpoint as our last one, and we're going to have an upward 750 newtons, and you can see that because our Ry is positive, so it's going to go in the positive y direction. And the equation for this is going to be shear equals VQ over I and then T. V being the shear force, Q, which is going to be our Y bar prime, times our A prime, I, which would be the moment of inertia, and then we're going to have T, which will be our thickness. So the problem here is our point A from this point is going to be right here, A. And Q is going to need that area along where the point is, and we don't have any area on our outermost fiber. And so Q is going to equal 0, therefore our shear is going to equal 0, our shear stress. It's not really a problem, actually saves us time, but it's something to be aware of. We don't need to draw stress blocks because we didn't have anything acting upon it. And so what we will do is we will move forward. I will have the picture come here. We'll move forward, right. Great. And so now the next one we're going to do is we're going to start and find our transverse shear using our R of Z which should yield a shear stress. And so we're going to draw our cut diagram. And now we're going to have in the x direction and the z direction. And so we're going to be looking above from the beam, which is important, which I will explain. And so because of that, our point now will be in the middle on the neutral axis, point A. And using our R of z, that was a loud noise, using our R of z, which is negative 500 newtons, it's going to go in the negative direction of z, which is upwards, 500 newtons. So we're going to use that same equation, shear equals VQ over IT. What we do know is V is going to be our shear force, which is going to be that negative 500 newtons. We can say that looking at the cross section from this point, we're going to have it to be here. If you cut it right here and look, you're going to have our neutral axis. We're going to have our point right here, which is going to be our y bar prime. We're going to have our area, which is going to be our area prime, that's going to help us find our Q. We're going to have our thickness, which is still going to be the 0.032. And then we still have that length, 0.060 meters. So let's find our Q. Our Q is y bar prime, area prime. Well, our y bar prime is going to be half the distance from our outermost fiber to our neutral axis, and we have the full length, and so what we can do is have our 0.060 divided by 4. 0.060 divided by 4. It's going to be 0.015, but I do want to explain that. Then our area is going to be our shaded region, which is just going to be our base, 0.032, times our height, which now is going to be half of our normal length, 0.030 meters. That will yield a Q that equals 1.44 times 10 to the negative 5 meters cubed. Now we have to find our moment of inertia. For a rectangular section, our moment of inertia is going to be 1/12 base times height cubed. And this is going to be for the representation we have for it, which is important for later on when we use a moment of inertia when we have it the opposite way, or have it rotated at 90 degrees. And so for us here, it's going to be 1/12 times the base, 0.032, times our height. This is going to be our full height, 0.06 cubed. This will give us a moment of inertia of 1.64 times 10 to the negative 7 meters to the fourth. We already said our thickness is 0.032 meters. Now we have enough information to solve for the shear stress. So we have our shear stress, VQ over IT, so we're going to have negative 500 newtons. We have our Q, 1.44 times 10 to the negative 5 meters cubed, divided by our mode of inertia, 1.64 times 10 to the negative 7 meters to the fourth, times our thickness, 0.032 meters. That will give us a shear stress of negative 0.391 megapascals. And so for writing our stress blocks, this is going to be in the negative direction, and it's only going to be on our XZ plane. And so since it's negative, we will have it in this direction. And why it's that way is when you have to think of the cut, when you think of it negative, it's almost like a negative slope. And so if it was to be positive, then it would be going this direction. But because we have a negative, we have the arrows for the cut pointing in this direction. And this is going to be negative 0.391 megapascals. Now we're going to use our moment around the x-axis and the torsion to find more shear. And so we're going to use our rectangular section, cross section, looking inward. So this is our y direction. This is our z direction. And using the moment known, we're going to see if we can find our shear, which is going to be the torque times the distance to the outermost fiber divided by our J, which is our polar moment of inertia. Now the problem is for our mx, we can see up here, our mx equals 0. That's going to make our torque equal 0, and ultimately make our shear stress equal 0 as well. And so there's no torsion. We don't need to write our stress blocks because our shear stress equals 0. And so now we're going to move on. We're going to use our moment around the z direction to find bending. So we're going to make another cut. We're going to have x, y. And so we know from this angle we have our point A to be at the top. And we have our z moment to be 135 Newton meters. That's going to be counterclockwise. 135
Newton meters. Great.
And then, so we're going to have our stress be our moment times our distance to the outermost fiber divided by our moment of inertia. And so for this, we're going to have our moment, which we already have, to be 135 Newton meters, times our distance, which is going to be for us that half distance from here upwards, because we're looking at it from this direction. So if this is half, it's going to be that same length, which is for us going to be the 0.016 meters, or 16 millimeters. And that's going to be divided by our moment of inertia. Now this is going to be a different moment of inertia from up here, because our representation is going to be from this cross section. And so instead of having it as this, we're going to have it from this cross section. So now we're going to have our, move this forward, 1/12, and we're going to have our base 0.060 meters now. There's our height, 0.032 meters cubed. That's going to give us stress of 13.18 megapascals. So now, I'm going to move this over here. We're going to draw our stress blocks. We're going to have this in the x direction. So for both of these blocks, we'll have it 13.18 megapascals, 13.18 megapascals. Cool. And so now we're going to find our last one, which is going to be our moment around the y-axis for bending. And so we're going to have a cut diagram. And we're going to have this in the x direction, and now we're going to have the z direction looking above. So now we're going to have point A along the neutral axis. And for our y moment, we're going to have a positive 110 Newton meters. And so we're going to have counterclockwise 110 Newton meters.
As we seen, yeah.
Great. And so for this, we're going to have same concept. We're going to have our stress equals my over I, but we have our y, which is the distance to the outermost fiber. Well, we have our point A to be along the neutral axis. So our y is going to equal 0 because point A is on the neutral axis. And for that reason, now we have our stress to be 0. What to do? And so now the stress blocks for those is going to be non-existent. Our next step is to combine our stress blocks. And so what we're going to do is we're going to add all the actual given stresses that we've gotten. We have our axial stress, flip it. We have our transverse shear, and then we also have our stress that we just found. Put that here. And so that's going to give us right here x, y. Combining them, we will combine our x, which is the 5.208 megapascals, and we're going to add it with our 13.18 megapascals, which will give us, both in tension, we will get a 18.388 megapascals. And then we're going to get for our shear, it's just alone, but we have our shear to be the negative 0.391 megapascals. Kind of messed up. I'm going to put it right there, but that megapascal's got in the way. We're going to have 0.391 megapascals. So we're going to use our x and z plane because it has both our shear and our axial force. And so now we're going to find our principal stresses. And so I'm going to get another piece of paper for that. There you go. Principal stresses. So the equation for this is going to be our sigma 1, sigma 2 equals, or sigma 1 plus sigma 2 over 2, plus or minus sigma x, or no, sigma 1, sorry. And so we're going to have sigma 1 minus sigma 2 over 2 squared, plus our shear, and it would be the 1 or 2, x or y direction, so whatever plane it is on, squared. And so for this, we're going to have our sigma 1, sigma 2 equal the 18.388. I'm going back to pascals. I don't need to, but I just feel more comfortable doing that. But so I messed up. Sigma 1, sigma 2 equals 18.388 times 10 to the 6 plus 0 over 2 plus or minus the square roots 18.388 times 10 to the 6 minus 0 over 2 squared plus our shear, which is the negative 0.391 times 10 to the 6th PA squared. And what that's going to get for us is we're going to have 9.194 times 10 to the 6th plus or minus 9.202 times 10 to the 6th. Sigma 2 equals that. So sigma 1 is going to be the plus, and our sigma 2 is going to be subtracting each other. So sigma 1 is going to be our 18.40 times 10 to the 6 pascals, or just 18.40 megapascals. Sigma 2 is going to be negative 8,310 pascals, or negative 8.31 kilopascals. And then our shear is going to be everything after the plus or minus. So it's going to be our square root right here, otherwise just known as our second number that we have within our plus and minus, which is going to be 9.20 times 10 to the 6th pascals, or just 9.20 megapascals. And that is how you find your principal stresses and your shear stresses using combined loading, using this given beam. And a signature to show I am me. Oop, that's not a straight line. Oh well. Brady Johnson. Awesome. Thank you.